All right, cool. Thanks everybody for coming to this talk. This is Dhairya. Close enough, right?
Yeah, yeah.
I'm
No,
sorry. And this is Julian, and they're going to talk today about training Llama 2 in Dagger.jl, and you guys use Flux, is that right? Yeah, so this should be a very cool talk because this is not a thing that we normally do in Julia. So I'm excited. Yeah, good luck.
Thank you.
Thank you.
All right. Hey, everyone. Microphone. There we go. So I'm Julian Samaroo. We've been working on training Llama 2 in Julia with Dagger.jl and Flux.jl.
So that's our little llama that hopefully by the end of this talk we would have trained to do something interesting, right? So the first question is why? Why would you want to do that? Everyone uses PyTorch anyway, right? There's a very, very big ecosystem of models that are trained to perform many, many specialized tasks already existing in the Python ecosystem, along with a lot of tooling to actually help deploy them as well as fine-tune them on various other tasks as well. So why do we want to go ahead with Julia in this case? Well, the tooling in Python is not perfect. A lot of these tools that we do see don't actually interact with each other that well. A very common example could be something like trying to use Number with Torch. Up until recently, doing that was also quite hard, and the setup involved was extremely non-trivial. Especially if you want to do anything at scale, that means that you now have extra overhead, so to speak, to actually set up the various libraries and the binary dependencies that come with setting up a large training routine. So while PyTorch is great, it has many available operators, it is completely GPU capable, well tested. The GPU support, unfortunately, is super inconsistent. While it is possible that you have something as cool as NVIDIA working, but support for AMD, for example, which is, again, a big vendor, is not really there yet. It's very difficult to write generic code, and even the generic code that we do have often comes with compromises of its own. As is very commonly known, Python front end is backed by a lot of C and C++ underneath it.
And also just pointing out, CUDA and AMD, or NVIDIA and AMD, are not the only two GPU vendors. We also have Apple GPUs. We also have Intel GPUs. Support for those is meh.
So Python does come with its own challenges, right? As we spoke about earlier, Python packaging is kind of a mess. Actually getting the package manager to cooperate is itself a bit of a task. Python itself might be slow. It needs the tool language problem to actually be performant by for modern machine learning tasks at this point. It is also extremely hard to write new operators, as we spoke about. The amount of boilerplate as well as setup code required to actually make Python do anything fast is pretty hard. Multiprocessing and multi-threading story in Python is slowly evolving, but at this point, it is something that is much, much easier to do in Julia as it stands.
So maybe we should just use Julia. So what is the state of Julia's Llama 2 support? So we do have Llama 2 packages in Julia. There's llama2.jl, there's transformers.jl, there's some other ones I'm not remembering right now. They have support for inference. There's support for training on CPUs. Maybe transformers.jl has support for GPU training. Not really out there, not really been well tested. Transformers.jl is great. It has a lot of flexibility. It's got a lot of, you can build your own LLM models with it. It's quite verbose. It's not something that you're going to do in maybe 20 lines. And no quantization support. What specifically you can load, at least with llama2.jl, you can load quantized GGUF weights, but you can't actually work with them in memory or on the GPU. You have to dequantize to float 32 first, so that is quite unfortunate. So what do we do?
So let's talk a little bit about the trends in how machine learning workflows in the modern age have actually grown. So as we can see, this is a graph that shows the size of the data sets that have been trained over time, starting from about the 80s, late 80s till modern day. We can see a large spike at the top right, and this actually happened very close to when quantization support was something that was featured more heavily in training routines. As we can see, very clearly it shows the hunger for more data, for bigger models, and with that comes the necessity to actually manage this much data, manage this many parameters in our models. So how do we actually tame this beast? Well, quantization is therefore a very, very big need at this point for us to actually scale our training processes beyond a single node GPU. This leads us to the next point. How do we actually go about parallelizing our training processes? We have many options, but knowing that we have an ever-increasing number of parameters in our models, an ever-increasing amount of data that we need to train on, and super specialized tasks that go with them, how do we actually decide what is the most scalable manner for us to train modern machine learning workflows, especially in the presence of non-standard training routines?
To start with, right, before we look at the various ways that you can actually parallelize things, parallelize large language models or other machine learning AI models, just to point out, we said before that this is using the work that we're doing is using Flux JL and Dagger JL. Flux JL has great autodiff support via Zygote.jl, has this fmap helper that we'll see a little bit later for applying functions and operations to all of the gradients in a model. Quite convenient if you've ended up using it. It comes with quite a lot of general purpose machine learning utilities, various losses, optimizers, like the kitchen sink, everything is in there that you need. And of course it's GPU enabled. This is providing basically our machine learning AI scaffolding for what we're going to be doing. And then Dagger.jl is basically providing task parallelism APIs that we're going to build on. Supports threads and workers, so multi-threading, multi-processing, has a cross-vendor GPU API. As I was saying before, there's not just 2 GPU vendors, there's at least 4. Support for all 4 of them is available and tested, and allows us to flexibly deploy training for basically most of the compute architectures you're going to see out there. So what are our possible approaches for parallelizing here? So there's basically 3, there's more than this, but these are the 3 most common. There's model parallelism, where, okay, maybe you have a branch in your model and you have 2 kind of independent paths that you take through the model when you're doing inference or doing training. So, okay, you can execute those in parallel. You can run one on one task, one on another. Maybe that's one thread, another thread, one GPU, another GPU. Then there's operator parallelism. So this is exemplified in, say, like matrix multiply. You use BLOS. BLOS is multi-threaded. BLOS can do, use GPUs, stuff like that. Various other operators support this. And then there's this third one called distributed data parallel, or DDP. So this one is what we're going to talk about today. Real quick, the first 2, limited parallelism. There's not a lot of cases you can apply model parallelism, and operator parallelism doesn't necessarily always get you that far. Both can bottleneck in quite a lot of cases. DDP, which we're going to talk about, is quite scalable.
Let's talk about what basically DDP allows us to do, right? The idea behind it is simply that we use some kind of already used collectives over large batch sizes across multiple devices, which themselves get synchronized together and then shared back to actually optimize our models. So typically you would end up with having multiple copies of the model on various devices. Each then gets their own data set or sort of a shard of a mini batch, which then together coalesces back to form a singular gradient, and then passes that back and uses that to update all the copies of the model. So this is a very, very common scheme and has been implemented many times in different forms. Its generalization is this concept of single program multiple data, or SPMD. Something like this is very predominantly used in MPI, and for that matter, even the GPU stack is built on very, very similar ideologies. So what are the benefits? It allows us to scale basically as many times as we have devices. So as long as we can keep adding devices and nodes, we can keep increasing the amount of compute we have and increase the amount of training we're able to do at any given point in time. Beyond that, it is quite simple to set up. The basic building blocks of SPMD, as I alluded to earlier, is quite easy to actually express, which means that we get a lot more flexibility in how we get to deploy it, especially in terms of in the presence of training routines that are not standard, and something like an LLM definitely doesn't count as a standard neural network, considering how much data we have to deal with. Managing all that memory becomes a big bottleneck.
And yeah, more and more models are getting ever more complex. So this is an approach that is scalable also into the future. Just real quick, what we have up here, sorry if the font is a little bit small. We have, this is basically just how we've implemented SPMD, or the core component to DDP, where basically you just have this SPMD region. You have a rank. If you're familiar with MPI or CUDA, in MPI, we call it a rank. And in CUDA, it's a lane or a thread. Basically, the idea is you get an integer index, which is unique to each thread and tells you what piece of data you're working on. So we have an API for that. And the idea we're showing here is basically you can just write your loop, walk through iteration by iteration, updating your variables locally. This is happening in parallel on multiple ranks. Those can be multiple threads, multiple GPUs, whatever. And then whenever you need to, you call a collective operation. And a collective operation is just basically saying all of the threads or ranks or whatever you want to call them all cooperate to update their values together because they depend on each other's values. In this case, we created an array X, and then we just did what's called an all reduce, just summing all of the values together and then just writing them back into X. Super simple operator, one line. So how does SPMD actually work? So the way we've implemented it on top of Dagger.jl just creates a set of Dagger tasks. Each task has its own rank, as I said before. And then during a collective reduction, as we saw in the last slide, it uses a highly parallel GPU-aware Dagger-powered ring reduce. Ring reduce is one of those very efficient ways to do an all-reduce operation. It is typically pretty hard to optimize, especially on like a supercomputer, which is where most of the research usually is. But it's difficult even across threads and GPUs. These are just kind of the system that this is built on performs very well in a highly parallel setting.
So what's missing at this point? We spoke about already having Llama packages. So we have Llama 2, we have language models.jl. We already have a Dagger-based API which allows us to implement an SPMD routine. Well, just add a little bit of data parallelism and there you go. I mean, what's really missing? Turns out not much and also quite a lot. Let's start digging into these things one by one, right? Llama2.jl, while a very, very capable package and actually is very highly optimized as well in terms of CPU compute, does not actually have support for a lot of training routines. Especially on the GPU, right? Because as we'll see later, managing this much data actually requires us to have a lot of parallel compute that's available to us. But if you were to go through this little piece of code right here, right, I want to also also want to highlight how simple this is and how familiar it might be to someone who's already written or seen, how a Flux training routine works. On the top, you basically start with some setup. So you load some data, you take your model, and we just have helper routines for that. You have your optimizer, and you set up that optimizer. This is pretty standard. Well, the next little bit is also fairly standard for those of you who've already written Flux routines, which is you basically start a loop, right? And in that loop, you typically have a loss, and you calculate gradients of your parameters over that loss, and then you optimize. Well, there's just one little piece of code that we've added in the mix, right? And this is where we actually do our parallel reductions. We spoke about why the fmap was helpful. Well, it just so happens that because we have these basically nested tree objects inside our gradients, we want to basically collect all of them, but not actually pause all the training, the loop that is actually going on, right? So we want to synchronize at one point in time, actually collect all of it, do a reduction, and then spread that back around. So as you can see here, our all reduce is basically just going to sum over all of our gradients and then do an average in this case. Very, very simple. And then our existing packages can just then update the model state, because even though this loop is actually happening in parallel, it appears as if everything literally was happening in a local for loop that we are all familiar with.
Oh, and quick comment. This is not specific to Llama 2. This loop is very easy to apply to basically any model. Yep.
Yeah, I should also talk about this routine is something that is not limited just for the packages that we've written or the models that we've written. They can be applied to downstream tasks just as easily as well. Of course, things are easier said than done, but fundamentally, the building blocks are all there, and the building blocks are generic, which means that even though we're just composing existing packages, we still get the ability to actually express any kind of model that you would typically as a Flux model, and then simply make it parallel by adding very, very simple primitives in the middle as well. So let's talk a little bit about the benchmarks. As I said earlier, Llama 2 currently only supports CPUs. Transformers doesn't unfortunately have support for the GGUF weights that we're going to be testing with, which makes it a little bit, it wouldn't be a fair comparison. And so it's really hard for us to compare across packages. And this was expected, but still quite a shock for me personally, because you would expect for an ecosystem which already we know has the support for these models, it is still quite in its early stages, and that is highlighted by the fact that we don't actually have a unified routine to manage all of these things and compare across them in a nice consistent way. So this is just a simple run that we had done for managing our training runs. You can see the model config at the top there. We used the weights and the pre-trained models out of Hugging Face, and this is effectively the config that Llama 2 would actually give you. Both those models were trained exactly with the same config on the same data set. As alluded to earlier, Llama 2 does not unfortunately have support for GPU training, so just as a reference, this is with the Flux model, but it's within spitting distance of the Llama 2 implementation itself. Important to note here, the first number that you see here is actually just the forwards pass for a large enough batch size, and the second number is for the reverse pass, the backwards pass. Whereas on an NVIDIA V100, because again we as long as we use array operations throughout, and LLMs use mostly just array operations throughout, we can benefit from existing kernels that exist for all of the various operations that we have to do, your multi-headed attention, your rope, and so on, positional encoding. So luckily, that means that we have a mature enough GPU ecosystem at this point that time per mini batch is pretty manageable at this point. We can see that we can genuinely, even on a single GPU, get a decent amount of performance. And because as we mentioned, this model is pretty scalable. As you add GPUs, you can actually increase the amount of data that you're passing through your model and naturally get scaling from there as well.
And we also expect that we can optimize these numbers a bit as well with a little bit more work. So this, at least for the GPU side, this can get better. Notably, there are some missing features. So we did discuss, well, I'll start with the second one first. We did discuss quantization support as being extremely important. That is another area where performance will improve over time. So this is something that we definitely would love help with. It's a good bit of work to implement the full support for all of the quantization operators that llama.cpp, kind of the like gold standard for Llama, supports.
So quantization support goes beyond just having a number type. Our ecosystem is basically written to be extremely composable, which means that we have a number of packages that come into play for the simplest of operations, and something like a large language model is definitely not, right? So we're talking that same support going from the highest level of abstraction from the model itself down to our AD, our kernels that we write, to actually having those operations implemented in the GPU backends, be that CUDA, AMD, and so on, as well as then within base Julia itself. Basically saying anytime we actually lose the quantization effects, that is to say, anytime we have to make a copy or convert to a large format, large floating point format, we end up with the same kind of performance that you would otherwise expect. Now, that is not a small or an easy task, right? It requires the entire community to come together to actually, basically chip away at the various pieces.
And then additionally, one thing we had not had the chance to get to was LoRA fine-tuning support. This is additionally something we would love help with. I don't believe Llama 2.jl supports LoRA fine-tuning.
Not Llama JL, yeah.
Yeah. Real quickly, the challenges that we went through when working on this: GPUs have less memory than CPUs, which exacerbates the problem that the GC doesn't always like what I do in Dagger and what Julia's distributed.jl does. I promise they're all regular, normal things. The GC doesn't like it. The SPMD implementation is pretty new. There is the potential for some deadlocks, and it's not always the most user-friendly, so we're working on improving that so it's easier for users to apply. Distributed.jl is buggy. If you saw my Dagger workshop on Tuesday, you're quite aware of this. And then Zygote can't auto-differentiate in-place operations, so our memory footprint and the GC issues that causes, it becomes a problem. This is something that we want to take a look at pretty intensely over the next few months. And then numerical AD issues are always kind of hard to debug.
One small point that I wanted to make was luckily this list of challenges is something that the larger community is aware of and is pretty commonly known, right? Like these are challenges that we all have faced over and over again in different forms in different places. So I do expect, over time, all of these things to improve quite substantially. So to conclude, basically what we ended up doing was we have now a Flux-backed Llama 2 implementation, which means that it is doing things a little bit out of place, but more or less is able to compose well with downstream packages that also allow usage of Flux models or just functions in general. We implemented a pure DDP training loop, i.e. there was really no dependencies to speak of, and or setup for that matter. It was pretty easy to go from running on my laptop on CPU threads to putting it on a server which had a GPU, and then beyond to a node which had multiples. Luckily, this also means that we can therefore support basically any model that. Whoops, this screen just went. Okay, never mind. We can support basically any model, right? Because it is built on top of these composable building blocks, and basically any GPU backend that Julia has support for. Okay, so and finally, Llama can train with multiple CPUs and multiple GPUs. So we've spoken about that.
And just real quick, we would love help with all of these things. So if you're able to help out or really interested in learning how all of this works, we would love you to reach out and just give us a hand with this so we can make this really work super well and beat Python.
Okay, yeah, that's our talk. Thank you.
Okay, as always, yeah, if you want to help, if you have more in-depth questions, you can always find them after the talk and corner them and ask them all the questions you want. For now, we have time for 1 or 2 questions.
Hi, thanks for the talk. So building on what you said right at the end, do you have any idea how your training compares in terms of benchmarks with like PyTorch or JAX or some of those frameworks?
So again, the kind of comparisons that we would want to make were not very trivial. The same kind of issues that came up when we tried to compare across the Julia ecosystem, get exacerbated once we include Python in the mix, right? Because not only now do they have support for something like a quantization or a LoRA or whatever, the problem completely changes all of a sudden. So no, in our study we did not actually compare strictly against Python benchmarks, but that is purely because it would not be a fair comparison anyway.
Okay, thank you.
Other questions?
Thanks for your talk. Quick question. So assuming I have some cluster somewhere that has AMD, NVIDIA, Intel, and maybe some Mac connected to the system, could this already run the compute across these 4 different hardwares, given the abstraction?
The answer is, I will say technically yes. All of the infrastructure is set up to support that. I would say whether you're running multiple different vendors on a single system, or if you're just wanting to try out, a training run on one kind of GPU, a training run on a different kind of GPU, but keeping that all homogeneous, that should definitely be pretty easy to support. Works already. Everything that this builds on is supports all the 4 main vendors right now. So give it a try. If you run into trouble, just let us know and we can fix up anything we find.
That's great. Thanks.
I think that we can do one more question.
Hi. Well, thank you very much for the talk. It was very interesting. I don't know, maybe this question is more for the developers of Metal.jl, but since you were talking about the flexibility that Julia has compared to Python or to the other frameworks, I know that the ARM processors from Mac have a GPU, but also a machine learning processor specific that with all of this coming from AI everywhere, I think that the machine learning processors in the Macs and also in other computers will get larger, and it will be very convenient, and it will be a large advantage over Python, for example, if we could use that power. And I don't know if that will be possible at any time or not, or if it is completely different from a GPU.
Yeah, we are aiming to be as generic as possible with these codes so that we are able to hit dispatches within, say, metal.jl that allow us to use various tensor hardware, stuff like that, use vendor BLOS or whatever, whatever the most efficient and available thing is. So yes, definitely that is something that we can support with this. If it's not currently supported, I think it's just something, file an issue on Metal, and then the GPU developers can take a look at it and get that implemented. But all of this would be able to use that.
Okay, that's all the time we have now. There's going to be a short break, but do come back. There's going to be a series of 10-minute talks with more on AI after that, and then even more talks after that.